This is probably going to be the last video of new material for Unit 3. And I want to wrap up this unit by talking about quantum numbers. Quantum numbers are a set of numbers that can tell us where an electron is within an atom. Not only that, every electron in an atom has a unique set of quantum numbers. We'll wrap up Unit 3 with this. In Unit 4, we are going to continue talking about atomic orbitals, quantum numbers, and do a lot more practice problems. But here I just want to introduce quantum numbers. And actually, before I introduce quantum numbers, let me do a short review about atomic orbitals. Since the quantum numbers tell us where an electron is, it would be good for us to know pretty well the different atomic orbitals that can exist within an atom. This is coming from the previous video, 03K20, where we talk about the different orbitals. And what I'm going to do here is I'm going to list them. So the first orbital that we saw was 1s. And this is in what? Increasing energy. Remember, the 1 here stands for what? The energy level, or the n value. The n equals energy level. Later on, we're going to know this also as the shell, but let's not worry about that. That's the first atomic orbital. The second one would be 2s. Okay. The third would be the set of 2p's. And I am going to separate them by 2px, 2py, and 2pz, because I like to literally see the number of orbitals. Right now I have 1, 2, 3, 4, 5 orbitals. It's just that these last 3 orbitals are the same type of orbital, but in different orientations, the x, y, and z. That's where we stopped in terms of drawing the cartoon, the 3 2p orbitals. But I alluded to using the periodic table at the end of that video to figure out where the other orbitals come in terms of increasing energy. Here's the Unit 4 preview that I showed in the last video, and we're up to what? We're up to the 2p. Just by reading this cartoon or this schematic, the next is 3s, followed by 3p. So I'm just reading the periodic table from left to right. The next one is 3s, and the next one is the 3p orbitals, 3px, 3py, 3pz. You will get more practice with this. This is alluding to what's called the electron configuration. And let me just put a little note here. We're not going to draw or state the electron configuration formally. This is just an idea of what it is, because this will be in Unit 4. Okay. After the 3p orbitals, we have the 4s, and then we have the 5 3d orbitals. Okay. So the next is 4s, and then there are 5. I'm not going to name them X, Y, Z. Those names are a little bit tricky, and I never memorize them anyway. But there are 5, and we did say previously that the first d orbitals will occur in the n equals 3 energy level. Okay, you keep on going and you get to the f's, which we did not do in any video yet, and we'll stop here in terms of the review. Quantum numbers. Now we could talk about quantum numbers. There are 4 quantum numbers. And the first quantum number, the symbol is n. Let me see how I'm going to organize this. The first one is n. Okay. And that has a name. It's called the principal quantum number. All of these numbers will be integers. And it's not necessarily important that you know the name. What's more necessary is that you understand what the meaning of it is. N is the same N as we saw in the Bohr model, and Bohr called this an energy level. In quotes, you could call the N principal number, or the N quantum number, as the energy level, and I've been doing that for the past couple of videos. It's also called the shell. Let me put it here. There are many names for each of these quantum numbers. The last name that you would want to be familiar with is, it really describes the size of the orbital. Not the exact shape, but the general size of the orbital. Because remember when we discussed 1s versus 2s? See, here we have 1s, and this is still the s and or still an s orbital, but in the 2 shell or 2 level, and it's bigger. You can imagine 3s would be even bigger. And I actually had that printed out here in this figure. It's just a cross section, but we have the 1s, the 2s, and the 3s. So that's why the n principal quantum number can be, think of the size of the orbital. Now, what are the possible? The possible n values starts at 1. It could be 1, okay? So that was the ground state, right? For the hydrogen atom, n equals 1. 1, 2, 3, etc., all the way up to, for our universe, we have atoms where the n value is 7. That's as high as we've gone so far. Maybe in the future, with larger atoms being produced, larger elements, we could get up to 8. 1, 2, 3, all the way up to 7. That's it for the principal quantum number. The next one is going to be L. And I use lowercase or cursive L just to make sure that it's not confused with I or 1. Did I spell this right? There's an N there, principal. Next one is angular momentum, quantum number. I'm not going to go over historically why these names were chosen. Just remember this is the L quantum number. Now what's its nicknames? If this is an energy level, this is sometimes called the sub-level. The sub-level quantum number. Or if it's the shell for N, beneath it would be the subshell. But I like to think of it as the type of orbital. S, P, D, or F. Type of orbital. Just remember that when in a textbook, if they ask you what is a sublevel, you are giving them the quantum number for L, or you're just stating the type of orbital, S, P, D, or F. So here are the possible L's. L can equal 0, 1, 2, or 3, and that's it. Why? Because we have s orbitals, we have p orbitals, we have d orbitals, and we have f orbitals for our universe, our periodic table. They started with 0. I know this sounds a little bit strange, but we'll go over reasons and tricks to memorize what are the possible n's and the possible l's in just a bit. We'll also have tricks to memorize what are the possible m sub l's. So what's m sub l? M sub l is the magnetic quantum number. And in terms of its nickname, this really tells you, the textbook says orbital orientation. Remember that the p orbitals, there are three of them, px, py, and pz, for each energy level starting at 2. Well, the m sub L magnetic quantum number tells you which of these p orbitals the electron is in. Now, if your sublevel or your subshell is just s, there's only one s orbital per energy level. But remember, there are 3 p orbitals, there are 5 d orbitals. So to pinpoint where a specific electron is, we have to specify which orbital within the subshell does that electron exist. Or instead of saying orbital orientation, x, y, and z, etc., really this is just which specific orbital. So not the orbital type, which is SPDF, but which P, which D, which F. Possible M sub Ls is a little bit tricky because it depends on the orbital. Because there's one s orbital per shell, there's 3 p orbitals, there's 5 d orbitals, and there's 7 f orbitals. So what I like to say is that what's possible for m sub L is you take negative L to L. What does that even mean? Let's say that if, what color do I want to use? Let's use black. If L, this L right here, is 2, what does that mean? That means you have d orbitals, right? These are d orbitals. But which d orbitals? You know that there are 5 d orbitals, and to designate those 5 d orbitals, the m sub L possible can be -2, 1, 0, 1, or 2. You notice how we go from -2, negative L, to positive L, which is +2. It just turns out that if you show all the integers between those two integers, including those two, -2 and 2, you get 5. This tells you that there are 5 d orbitals. There are 5 d orbitals. It gets a little bit confusing because what is that 5? Is that 5 the number, the amount, or is that 5 the energy level? Well, I'm not talking about the energy level. I'm talking about the number of d orbitals. 1, 2, 3, 4, 5. Therefore, if you have, let's go a little bit easier. What if you have a p orbital? What if your electron is in a p orbital? That electron will have an L of 1 and an M sub L of either -1, 0, or 1. Right? That's the p orbitals. And I'll write that down here. If L equals 1, okay, your possible M sub Ls could be either -1, 0, or 1. The last quantum number, which I unfortunately don't have space on this page, is the M sub S. Honestly, let me just put it here. I'm going to cram it in here. M sub S. It doesn't really tell you about the location, it tells you about the spin. This is the spin, and the nickname is just a spin quantum number. An electron can either have a positive spin or a negative spin. Those are the two choices. And for the positive spin, you want to indicate that with a quantum number of +1/2. So there are only two choices, +1/2 or -1/2. Okay. If we zoom out, the first 3 quantum numbers tell us the location, N, L, and M sub L, and the last one, M sub S, is the spin, +1/2 or -1/2. Okay. I have a problem for us because a typical problem or a classic problem with quantum numbers is which set of quantum numbers is impossible? Well, how can a set be impossible? Well, What if you had an electron in the d orbital? And we know that the L equals 2. So, and we get that from up here, right? 2 represents the d orbital. Well, what is impossible? It's impossible to have an m sub L of 3. It's impossible to have an m sub L of minus 4. It has to be one of these 5. Okay? Let me put in boxes, actually, the tips. Okay? So for the m sub L, the tip is it's between and including the ends, negative L to L. But what about the possible L? This one's a little bit odd. Because if you have an n equals 1, we saw in the previous video that in n equals 1 energy level, there's only one orbital. That is the s orbital. Oh, I have it here. There's no such thing as a 1p orbital or a 1d orbital. So if your n equals 1, the only possible orbital you have is the s, so that means the only possible L is 0. If you have energy level 2, if the electron is in energy level 2, what are the choices? Your choices are either in an s orbital or a p orbital. So that's 1 or 0. So there's no such thing as an electron that has an n equals 2 and an L equals 2. Okay? How do we summarize that? The possible L's are 0 to n minus 1. What? What does that mean? Let me show you. If n equals 3, let's take a look at our orbitals listed in energy levels. If s equals 3, what are the possible types of orbitals? We have an s, we have a p, and we have a d. There's actually no such thing as a 3f orbital. So there are no f orbitals in the third energy level. The only choices are s, p, and d. So therefore, if n equals 3, your only choices are L equal 0, 1, or 2. That's where we get this equation. 0 all the way up to n minus 1. So n equals 3, so 3 minus 1 is 2. So L is the integers 0, 1, and 2 if n equals 3. It's a little bit tricky. This is one way to learn it, okay, to understand what is possible. Okay, let me give you an example problem. I'm going to list 3 quantum numbers. I'm going to ignore the spin because spin is always plus half and minus 1/2. Those are the only 2 choices all the time for every single electron. But let me give you this problem here. I'm going to give you a set of quantum numbers. And the set of quantum numbers are going to be n, L, and m sub L. N, L, and m sub L. Okay, again, we're ignoring the spin. And I want you to tell me which ones are impossible. If I could find my notes. Here we go. Okay, the first one. 4, 3, minus 2. The next, 3, 0, 1. The next, 2, 1, 1. So for each of these, we're gonna put a little check that it's possible, or an X if it's not possible, and maybe it'll be also good if we explain why it's not possible. 3, 1, 0, 3, 3, 2. Let's start with, well, let's do these 1, 2, 3, 4, 5 situations. For the first situation, possible or not possible? If we have an n equals 4, right? If n equals 4, what are the possible L's? L could equal what? It was 0 to the n minus 1. So 0 to 3. 0, 1, 2, and 3. So that is possible. So the next one, if L equals 3, what are the possible m sub L's? This is where you take the negative L to the positive L. So the m sub L's can go from negative 3 to positive 3. Oh my goodness, why so many? You know why there are so many? It's because L equals 3 is a f orbital. And I didn't list it up here, but you have 3 p orbitals, you have 5 d orbitals, you have 7 f orbitals. 1, 2, 3, 4, 5, 6, 7. Okay. And then negative 2 is right here. So what are my numbers? I have 4, 3, and negative 2. All of them can exist depending on what is the quantum number before that. Right? N equals 4, you have these possible L's. L equals 3, you have these possible m sub L's. We're going to put a check mark here. What about this next one? 3, 0, 1. The way I like to think about this is if n equals 3, L can equal what? L can equal 0, 1, or 2. So there's 0, and there's 0. What do these represent again, guys? They represent the s orbital, the p orbital, and the d orbital. So yeah, in energy level 3, there is an s orbital. There is an s orbital. Again, in energy level 3, we have s orbitals, we have p orbitals, and we have d orbitals. There are 3 types of orbitals. That's why there are 3 possible L's. Now, L equals 0. If L equals 0, m sub L equals what? Negative L to positive L. But L equals 0. It's not even 1. There's only one s orbital per energy level, so m sub L has to be 0. It can't be 1. It can't be 1. There's only one s orbital per energy level. 1s, 2s, 3s. Because of that, how can you have an m sub L of 1? This will indicate, right, that you have at least 2 different types of s orbitals, right? Over here, as a comparison, we have 3 different types of p orbitals, x, y, and z. That's where you could get multiple numbers for m sub L, when you have the same type of orbital, but different orientations. Okay, so that's an x. You see the process here? So if you want to pause the video, do the next 3, either put a check mark or find the quantum number that is impossible to exist for that set. Pause the video and try that. And when you've had some guesses or your answers are listed on your paper, go ahead and unpause. Okay, real quickly. 2, 1, and 1, that is possible. Okay, that describes an electron in an atom. That an electron can have these set of 3 quantum numbers. Energy level 2, what orbital is this? The p orbital, and it's the third p orbital in the set of p orbitals. Next one, 3, 1, and 0. Energy level 3, and we have that here. Okay, the possible L's are 0, 1, and 2, so we have that there. And yes, a p orbital, right? If L equals 1, m sub l can equal -1, 0, and 1. So there's 0 for that one. That one's possible. The last one, if n equals 3, which is this 3 I'm talking about, what are the possible L's? It goes from 0 to, again, 1, or sorry, n minus 1. That's how you figure out the possible L's. Start at 0. So the possible L's are 0, 1, and 2. Because in the third energy level, you only have S, P, and D. There is, again, no F in n equals 3. Oops. See, this is the F orbital. That stands for F. That is impossible. There is no F orbital in the third energy level. Now for 2, well, it doesn't matter. This is already wrong, but if there is an F orbital, you can have a 2. See, here are the F orbitals: -3, -2, -1, 0, 1, 2, and 3. I know it's kind of at first convoluted, and the importance of this is a little bit abstract. For me, the importance of this is to indicate that when you have an atom that could have, maybe 30 electrons, each of those 30 electrons has a unique set of quantum numbers. Each electron in an atom has a unique set of quantum numbers. That's the end of Unit 3 in terms of new material. I may post videos after this looking at practice problems, but this is the last of the new material. Unit 4 is so closely tied to what we learned in Unit 3. Atomic orbitals, quantum numbers will have more practice in Unit 4. So if this is a little bit unsteady, you're unsteady with this, in the next unit, you're going to start applying these concepts, and these will become more solidified in your mind.